But seriously, if somebody was sitting on the second hand, like a little Lego man, how fast would they be going? It's kind of like a Ferris wheel ride. How fast would they be going? Now, this problem is referring to something called linear speed. Okay, and sometimes when kids start paying attention, like, wait, linear? I thought we were going in a circle. Okay, well, it's still a speed that involves a distance that I'm traveling and a time. So it's going to be called linear speed, just like if you were speeding down the highway. What's your speed? Okay, the question here is, well, I guess the question is how fast are you going, but we'll figure out what that has to do with radians. That also has something to do with radians. Here's one more. Now, at this point, you might be like, I don't know, Miss Naylor, can you just show me? But what I'm trying to do here is help you realize that these are two different ideas, and this is what kids get confused. So just listen to this. This is not referring to the same thing as the Lego man that's sitting on the Ferris wheel. This is referring to an angle, and it's literally referring to how fast is that angle growing? How fast is that angle rotating? Okay, and that's called radians per second. In other words, angles per second. That's a different idea than how fast am I going if I'm sitting on the outside. And I'll show you why. Okay, we'll show you why, but you just want to realize they're different. Now, on page 253, there's a little reading. And like, I really want you to do that. I want you to read the top of 253. I'm not just like wasting time here. I want you to read and write what you think is important. I bet you're going to write something about a formula. Keep reading. So you're just reading at the top. And again, I encourage you to write what you think is important. And again, I bet you're going to write something about a formula. Now, after you're done reading the top, I'd like you to look at example 5. Just kind of look at it. Don't worry, you don't have to understand it all, but beginning to read this will get you to that next step. So look at example 5 once you're done writing and stop at the blue box. Stop at the blue box. Now, when you read example 5, you might not need to write anything down. I kind of want you to learn how to, look at an example and just see what's going on in there. Now, we're going to write some stuff down. We're going to do an example. Example 5 is already written, so just kind of read it. I'm not saying you have to understand all of it, but there should be some things that you're starting to see based on what you read about this formula. And then stop at the blue box. Now, some of you, after reading that, you might be like, I got it. I'm ready to go. Honestly, most of us are not gifted with those genes. And I want to kind of help you. Okay, what did we just read? And maybe as I say a couple things, you're like, yeah, sounds good. It's making sense. But let's just kind of go back to the beginning, because sometimes I find that people are like arc length. And then it's like, that's just some, I don't know, sort of math garble. Arc length is a distance around the outside of a circle. The distance now could be a partial distance, okay? But when we say an arc length, we're talking about some type of distance around the outside of a circle. And look, it can be defined as a radius times a central angle. Pretty straightforward formula. Okay, now maybe like, where'd that come from? We'll kind of show you with another example, but I want you to realize something. Did you catch it? It has to do with the central angle. Okay, this would be kind of like one of your first pretty important nuggets of knowledge here. The central angle has to always be in, Devin? Radians. Okay, now, let's let's look at that example 5 just through a slightly different lens, maybe like you hadn't seen it before, and you just kind of started plowing ahead with example 5. You see that they're plugging in 4 for the radius. Okay, kind of makes sense. That's what they gave you. And then what if you kind of just plowed ahead and said 240 degrees? Now, that's not what the book did, but I want to make sure you realize how silly that would be. That would be like saying that the arc length is 960. You say, why is that silly? Well, if I have a 4-inch radius, is actually a little bigger, but if I have a 4-inch radius and I spin around 240 degrees, so like literally on the chalkboard, that is about that big. 960 inches? I doubt it. Okay, so it doesn't work in degrees. But it's really interesting. It does work in radians. And as soon as you change to radians, you get a number that makes sense. Maybe, again, now that I mention it, you hadn't thought about it, but yeah, 16 inches. Is that kind of what the book got there? Okay. I know it's just a quick chalkboard sketch, but that looks a lot more like 16 inches than 960. So you got to be in radians. Here's the cool thing about radians. They're able to take angles and I'll say convert them or turn them into distances. So a certain angle is able to be turned into a distance. It's like a little segue between those measurements. And of course, I'm talking about an arc distance. How about our clock? How about our clock? Okay, this was kind of the first question. No, that's not our clock. That's a problem for you guys to try. My fault. Let's try this. I thought I was somewhere else. Let's just try this problem. Now, just kind of a by the way, this is how I'll disseminate a lot of notes, using the screen and stuff. You have to copy it all down. I kind of say this a lot because I don't want you to sort of lose time by writing everything verbatim. Maybe you just kind of bullet point it, like find the radius. Okay, that's like the question, find the radius. What else do we have here? We have a theta. So I'm just kind of pulling that out. And, we were given an arc length. So I'll pull that out. Now, it's your notes, it's your learning, but I want you to use your time wisely. So maybe you can just kind of pull out the bullets here. Okay, now we're going to use that formula. And maybe you kind of jumped in here and started doing this already. Great, keep going, but we're going to use the formula because it relates the arc length with the radius and the central angle. Who doesn't like a formula now and then? You just plug into them. And I mean that, you plug into them. But you do need to be aware that you plug in radians. You plug in radians. So we have a little bit of a crucial step in this problem. You've got to change 330 into radians. Now this kind of takes us back to maybe the first, second, third day of school. If you want to convert to radians and you want to use this method I showed you, it's simply a matter of canceling the degrees. And the way that you cancel the degrees is by putting 330 in the numerator. That'll cancel the degree symbol here. Now I understand that's like a number that we're not real familiar with. It's kind of like, what is that? If you reduce it, I believe by 30s, if you reduce it by 30s, you get 11 pi over 6, which, by the way, is the same as 330. But you can plug that in for theta, do a little magic, and solve for r. Try it, make sure that it's working for you. You should get like 5.7. Make sure you play along, that you're able to just do what's needed to get 5.7. Now that would be the radius. That would be the radius. Anything that happened here, you guys, you're good for questions, so we're not in a rush. So if there's anything that's happened here, please ask. Okay, so that would be the radius that matches with that angle and that arc. And remember, an arc is a distance. It's a distance around the outside. But of course, for this problem, it was like a partial distance. But that size radius is going to create that arc. Now I'd like to look at the classroom clock. And this is more of a problem that I'd like to pause and let you think about it. Try to find something you can start with, even if you just wrote this down. That's something to start with, okay? Because that's the formula that relates arc with a radius and an angle. Owen?
Is it circumference formula derived?
Yes. Yes, I want to kind of bring everybody on board with that little aha moment. So let's put some numbers in here. Okay, now, did you guys put in 8? Start with something. I expect that you put that in. But here's kind of the big one. What is theta? What theta matches with a minute? What theta matches? Everybody should know. It's 2 pi. Now, when we write 2 pi right here, that's the angle. That's the angle that matches with a minute. I mean, if you need to kind of tell yourself what we did. It wasn't just random that we put 2 pi. And it's also not random what we now have. Now, I know you see it, Owen, but again, I want everyone to see this. We have 2 pi r. We have 2 pi times r. What's 2 pi times r? From your geometry class, that's the formula for the circumference of a circle. Does it ring a little bit in your mind? The circumference of a circle is 2 pi r. Now, here's the aha moment. That's why 2 pi is in that formula from 8th grade or 7th grade or whenever. That formula had a 2 pi because why? Because that is the angle that goes with not just a minute, but it's the angle that goes with 1 revolution. It's the angle that goes with that theta. Okay. By the way, the answer to this would be 16 pi. And it's inches, I guess. Yeah, it's inches. We should label it. Okay, so 2 pi. Not random, but it's theta. And it matches with a full circle. Now, this is arc length. Okay, about ready to kind of show you something else. And here's the part where, just to be honest, it continues to get a little harder if we let it, but just try to focus. We're now going to talk about some speeds. Okay, in the blue box at the bottom of 53, there's some statements about some speeds. I would imagine you want to write something down. Do that. After you read the blue box a time or two and write something down, there's an example on the next page. I guess it would be example 6. Take a look at it. Just kind of look at it. Example 6 on the next page. So look at example 6. No doubt it gets a little more, it's a little harder to understand, but at least give it a first look. It's a starting point. Just like we did before, I'd like to just kind of go back, give you a chance to listen to something. You might hear some of the same things. I actually want to even go back a step further that will answer for some of you, like, where did this come from? Because again, I don't want to be a teacher and just say, here's a formula, use it. Okay. Yeah, you might be able to use it, but you won't have any idea really what it means, where did it come from. Distance equals rate times time. Okay, I'm kind of using that as a starting point. I know you guys have heard that. You understand that if you have a rate and you multiply it by time, you get a distance. It's actually kind of what's going on here. We just have to adapt what we think of as a distance. Okay. Now, I got to step ahead of myself. If you solve this for r, you have a rate version. Now, I'm also kind of saying, hey, everyone should know that distance divided by time is a rate. That's exactly what's going on with these formulas, except we have to think of the word distance a little differently. Instead of it being a distance like from here to your house, the distance is an arc. Now remember, an arc is just like a length around a circle. So we're talking about a distance divided by time. Okay, but that's going to give you what you wrote down to be called linear speed. Okay, it's basically, again, a distance divided by time. What if we change the word distance? What if we change the word distance to be more like an amount of angle that you make? An amount of angle is a central angle. And when you divide that by time, you also get a rate. You wrote that down as angular speed. So these are speeds because they're divided by times, but they're like distances divided by times. One of the distances is around a circle. The other distance is an angle that you make. These are two different things. It's sometimes hard to get to understand that, but let's talk about some examples to do it. Now, instead of talking about example 6, I want to do another problem because I just feel like it would be helpful if you see some other numbers. So this is like example 6, but I want to show you with some other numbers. It's actually our Lego guy. Okay, how fast was he or she going? Now, it's very common to look at this and be like, okay, so like I need some more information. Let's talk about it. Okay, because actually all you need is a distance, in other words, an arc, and a matching time. Now, did you hear how I said that? You need a distance and a matching time. Do you know any distances about that clock? Do you know any distances?
It's that. But like
Now, what is that? Hold on. What is that? So it's the full distance, right? Let me just kind of go with that because listen, now you need a matching time. This is like the crux of the problem. What time matches with a full distance? What time matches? Now, if you're like, does he want it in seconds or minutes? Seconds. We want it in seconds. So let me ask it again. What time matches with a full distance? Justin? Remember initially, maybe you looked at this and thought, I need more information. Well, I get it. You just have to think about what you know. Now, some of you, you're going to look at this and like, when you look back at your notes, where'd that come from? Where'd that come from is, I know it's over here, but it's the arc. It's 8 times 2 pi. It's radius times theta. And here's the part of the lesson where that obviously connects to something we did a few moments ago. You got to make that connection. So this numerator is a distance, but it's an arc, and it came from that formula. Now, Owen, I really didn't want to sort of shut you off, but you said, did you want or?
Yeah, I found that what it is without the pi.
Okay, hey, great. In fact, what is it, 5? Oh yeah, sorry, a 5 was some other answer today. The answer to your question is if you would like to. Some people write this answer and they'll understand that that's the same as 50.25 inches per second. You can write it either way. I just want you to understand that it's a rate. It's amount of distance divided by a time. Now what that means is if you're sitting on the end of that second hand, you're going for a little ride. You're going 50 inches every second. Woohoo! Okay? 50 inches every second. I used to work for a carnival, not a circus, a carnival, like the York Fair or, like little Dowstown Carnival or something. So almost every ride was based on circles. How many different ways can you make something spin around and get somebody sick? So the answers would have varied. I wasn't thinking about that stuff at that time. Angular speed. How you doing? Are you kind of fried yet? I'm going slow because I want to give you a chance to think. And you're going to have to keep thinking tonight. Angular speed. Start with something. Start with something. What the heck? Why do I have 8.84 up there?
I gave you the answer is 16 pi, and it's like.
So anybody else wondering what was going on?
I was gonna correct it, but then I was like, I didn't want to interrupt. So. You were like telling a story, and I didn't want to fix it.
I'll be honest, at the time I was kind of like, I was sort of wondering the same thing, but I don't know, I just went with it. It was a lot of inches per second, which would have been really fast. That's what kind of made me think about the carnival, but it's not that fast. I mean, it's sort of you're poking along. All right, so it's not even an inch per second. Angular speed. Understand this. It's not the same concept. It's not how fast is the guy going around. It's how fast the angle is being made. How fast is the angle being made? We need an amount of angle and a matching time. You might be able to answer this. Don't call it out. Let people think about it. Do you know an amount of angle that's made in a certain amount of time? Do you know an amount of angle that's made in 60 seconds? Claire? 2 pi radians are created every 60 seconds. Does anyone know an amount of radian that's made every 30 seconds? Now, do you get the gist here? As long as you have a time that matches with an angle, you have the angular speed. And if you reduce this one correctly, which is sort of a little harder to understand, but you get like 1/10 of a radian every second. Now, 1/10 of a radian would be like this. 1/10 of a radian, kind of like the alligator song. But you're making 1/10 of a radian every second. That's how fast that thing is opening, to say it that way. Oh, shoot. 10:41. I don't know why I thought we had a few more minutes. This is just you're not going to be able to do this in 1 minute. We went a little slowly, which I think is helpful because you have examples. I wanted you to think about something in the classroom. If you want to take a picture of that, or if you want to still have that as an example, I'll even show you the answers. But I don't want to frustrate you by doing that. So use it as you want to. You still have the knowledge to look at the homework. Make sure you do that. Maybe we look at this problem. We can do that. The mini check tomorrow. Oh, did I say mini check tomorrow? Okay. It's on the calendar. It will not cover this. That wouldn't be fair. We need a little more time to process this. But there is a little mini check that covers kind of these first days of intro topics, excluding this. Okay. All right. Just want you to do a nice job on that tomorrow. Get off to a good start. So let's go over these 2 examples. I want to make sure that you have how to solve them, that you can see how to solve them. Now, you can start with either one of these. In this case, I did have angular speed first. And what I would say to you is you want to find a place that you know. I hope that you know the formula. And the formula for angular speed is some theta in some amount of time. Okay, so what we need some type of theta with some amount of time. Now, most students will say, okay, it looks like we know 2.5 seconds, so that's the time I should use, right? Right. Okay, the question is how much theta, how much angle is made in 2.5 seconds? And since it says here that it makes one full revolution, we use 2 pi again. So there's 2 pi radians in 2.5 seconds. Okay, a lot of times students will at this point say, do we always use 2 pi? And my answer to that is if it's one revolution. But what if I give you a problem that involves some other amount of revolution? You always want the pi to match the time. In this case, the time is 1 revolution. So we use 2 pi. And when you turn an answer like this into a decimal, let me see if I can find it here. You end up getting 2.51 radians per second. You don't have to turn into a decimal, but for those that do that, that's like saying that you're going to get 2.5 of those angles every second. All right, linear speed. Again, find a place to start. I know this is hard, but a place to start is the formula. The formula says arc divided by time. Okay, so basically I need a distance, I need an arc that relates to some amount of time. 2.5 is the only time that I have. So now the question becomes how much arc do I make in 2.5 seconds? Okay, now an arc from the beginning of the lesson is a radius times a theta. I just need to I need to plug in a radius 10. Don't use 20, use 10. So I need to plug in a radius and a theta. Okay, now here's what you got to realize. The theta you plug in has to give you the arc that's going to match with this time. And so since we're looking for a full revolution that matches with this time, we need a full arc. So we need a full 2 pi. 20 pi is your arc, your S. So end up with 20 pi. Now this would be in inches, right? This would be in inches per second. And if you divide that out, that means that you're getting 25 inches, 25.13 inches per second. Careful, we don't always use 2 pi, but we do always use a theta that matches with our time. All right?